Hello, this is Joseph Vadalero presenting the third lab of the spring 2021 semester in Physics 2211. The goal of this lab is to apply Newton's second law and other fundamental physics principles, such as universal gravitation, to analyze the orbit of a star around a black hole. We will then use this data in order to find the mass of the black hole. To do this, we will find the values of net force, the perpendicular component of net force, and the parallel component of net force for this unique seed. We will do this through the GlowScript IDE. The fundamental physics principles that we must use and understand for this lab are Newton's second law of motion, Newton's law of universal gravitation, the momentum principle, and the parallel and perpendicular components of net force. These equations are, respectively, final velocity is equal to the initial velocity added to the quotient of the net force and mass of the object multiplied by the change in time. Force is equal to the universal gravitational constant times the product of the two masses, all divided by distance squared. Momentum is equal to mass times velocity. Net force is equal to the parallel component times the perpendicular component of net force. Looking at my code from GlowScript, the first thing to notice is the unique seed for my star in orbit, which is just my email address. Next is the initial conditions for the gravitational constant, the mass of the star, the time interval, which in this case is 1 day in seconds, found by multiplying 60 times 60 times 24. Next, we want to notice the different equations inputted into the code. The initial and final momentum is seen as just the mass of the star multiplied by the initial and final velocity, respectively. The changes in velocity and momentum are found simply by subtracting the final value from the initial value. The derivative of momentum with respect to time is found by dividing the change in momentum and change in time. F net is simply equal to the value of dp dt. P hat, which is the unit vector for momentum, is equal to initial momentum divided by the magnitude of initial momentum. The derivative of the magnitude of p with respect to change in time is equal to the magnitude of final momentum minus the magnitude of initial momentum divided by the change in time. The parallel component of dp dt is equal to p hat times the derivative of the magnitude of p with respect to the change in time. The parallel component of net force is equal to the parallel component of dp dt. The perpendicular component of dp dt is equal to dp dt minus dp dt parallel. This makes the perpendicular component of net force equal to dp dt perpendicular. The next thing to notice is the calculation for mass of the black hole, represented by mbh. This is equal to the magnitude of net force times magnitude of the position squared, all divided by the universal gravitational constant times the mass of the star. The data for the mass of the black hole at each time interval is shown, as well as the average of the entire data set, being 2.03 times 10 raised to the 34th power. This comes from the magnitudes we found from net force and the respective perpendicular and parallel components of net force. These values are, respectively, 1.02045 times 10 raised to the 29th power, 1.01958 times 10 raised to the 29th power, and 4.81874 times 10 raised to the 27th power. On to some final questions for this lab. What is the difference between the change in momentum and net force? The differences between the two are apparent, as the net force is the sum of all the forces, and it can be thought of as what causes the motion of the star. On the other hand, change in momentum can be thought of as just the speed and direction of the object. So even though in the code they seem the same, they are indeed different. Imagine the black hole was replaced with a new one. Could the mass change? The answer is simply no. There would not be a way to tell the difference since the conditions are the exact same. It is not possible for the mass to be different. This can be seen in the fundamental principles discussed earlier, such as the universal gravitational equation from Newton.